No roads, no cars, no traffic lights. A city rising from desert sand, built for over 1 million people, and not one road in sight. Engineers call it impossible. Officials call it the future. The desert has other plans. Temperatures here can kill in minutes. Sandstorms swallow construction sites whole. Still, the digging continues. Something is being built beneath the surface. Something most people will never see. If this fails, billions vanish. If it works, every city on Earth changes. This is not a concept. This is already happening. And it almost didn't survive its first year. The site sits south of Dubai. Flat, empty, brutal heat. This is where the no-road city begins. Planners call it a walkable city. No cars, no highways, no exhaust. Everything reachable within a 5-minute walk. It sounds simple on paper. On the ground, it's chaos. The first challenge isn't technology, it's geography. The desert floor shifts constantly. Sand dunes move overnight, swallowing survey markers. Engineers lay foundation lines one evening. By morning, the dunes have buried them. A senior engineer flags the problem immediately. We're building on something that doesn't stay still. Stabilizing the ground becomes priority one. Crews bring in compaction machines, soil binders, geotextile layers. It works for a while. Then comes the heat. Surface temperatures hit 60 degrees Celsius. Workers can only operate in short shifts. Machinery overheats. Schedules slip. A project manager admits, quietly, "We underestimated this." But pulling back isn't an option. Investors are watching. Deadlines are public. So the team adapts. Night shifts begin. Cooling stations multiply. Progress crawls forward, inch by inch. Then, inspectors find something unexpected beneath the sand. Something that could change the entire foundation plan. They don't announce it yet. They just stop digging. Drilling stops without warning. Workers are pulled back from the trench. Underground, surveyors found something unstable. A layer of soft rock no one mapped. It runs directly beneath the planned foundation grid. If ignored, it could shift everything above it. An inspector studies the readings twice. "This wasn't in any geological survey," he says. The original blueprint assumed solid bedrock. What they actually have is far weaker. Every structural calculation now needs revisiting. Months of design work suddenly feel fragile. Officials are notified immediately. No public statement is made. Engineers debate two options: reinforce the unstable layer or redesign the entire base. Reinforcement is faster. Redesign is safer. Time pressure pushes them toward reinforcement. Concrete piles are driven deeper than planned. Some sink further than expected, hitting voids underground. One crew reports a section sinking unevenly overnight, a few centimeters, barely visible. Deeply alarming. If it spreads, the entire grid is compromised. A senior official orders an immediate halt. For 3 days, nothing moves. Specialists are flown in from outside the country. Whatever they find will decide the next phase. The team waits, tension rising with every passing hour. Then, new scans reveal something even stranger underground.
The new scans confirm a hidden cavity, empty space, sitting beneath the foundation zone. Not a void from drilling. It was already there, long before construction began. Geologists suspect an old underground water channel, dry now, but at once carved through solid rock. No one expected this far from the coast. An engineer stares at the readings, unsettled. This changes the load calculations completely. Building directly above an empty cavity is dangerous. Weight distribution could crack the surface eventually. One specialist warns of slow, invisible collapse over years. The team faces a brutal choice now. Fill the cavity entirely or shift the city's layout. Filling it means pumping thousands of tons of material underground. Shifting the layout means redesigning roads-free walkways already approved. Officials want a fast decision. Engineers want a safe one. Tension between both groups grows sharper by the day.
Look, we need to shut it down now.
A compromise emerges. Partial filling, partial redesign. It's risky. It's untested at this scale here. Crews begin pumping stabilizing material into the cavity at night. Sensors are placed every few meters to track movement. For the first week, readings stay calm. Then, without warning, one sensor spikes sharply. A small section of ground shifts again. This time, it's closer to inhabited construction zones. Workers nearby are evacuated within minutes.
Get out of the trench!
No one yet knows exactly why it moved. Workers stand back, watching the ground in silence. No collapse, no cracking sound. Just a slow, quiet settling beneath the surface. Engineers rush sensors and cameras to the spot. The shift measures only a few centimeters, small on paper, massive in implication.
The data clearly shows a major instability right under the proposed structure.
A structural specialist voices the fear everyone
before the
has.
next phase.
We don't fully know what's moving down there. Work pauses across the entire southern section. Investors grow uneasy. Officials demand answers fast. Behind closed doors, tension reaches its peak. Some push to abandon the underground-free design entirely. Others insist walking away now means total failure. A senior engineer proposes something untested in this region. Flexible foundation joints, designed to absorb small ground shifts. Instead of fighting movement, the structure would adapt to it. It's borrowed from earthquake engineering, never used for sinking sand. There's no time for lengthy trials. A test section is built within days. Sensors are buried deeper. Weight is added gradually. Every hour, the data is checked, rechecked. For 3 tense days, nothing moves. Then, on the fourth night, a storm rolls in. Heavy winds, shifting sand, pressure on the new joints. By morning, engineers rush back to the site. What they find determines if the entire project survives. Morning light reveals the test section intact. No cracks, no sinking, no shifting.
Looks like we finally got
flexible
clearance.
joints
Good.
held through the
Let's
entire
hope the weather
storm.
holds up for the pour tomorrow.
An engineer kneels by the sensors, exhaling slowly. It worked. It actually worked. Relief spreads through the team, but no celebration yet. One successful night doesn't guarantee a finished city. The design is scaled up across the southern zone. Months pass. Thousands of joints installed beneath the surface. Storms come and go. The ground holds steady. Slowly, walkways rise where roads once would have been. Buildings connect through shaded paths instead of streets. No traffic, no exhaust, no congestion. Just walking distance, designed into every block. What started as an unstable patch of desert becomes a model. Officials who once feared collapse now study the data closely. Other countries facing unstable ground take notice. This wasn't just about removing roads. It was about building safely where no one thought possible. The cavity is still down there, sealed and monitored. The sensors never stop watching, even now. Engineers call it a success, but they also call it a warning. Build smarter, or build somewhere you don't understand. This city stands as proof either path is possible. If projects like this fascinate you, there's more happening beneath the surface of the world's biggest builds. Some of it you've probably never heard about.